Okay. So today is the last section to cover for test 2, 2.9. So then Wednesday's class, this Wednesday will be a review. So I'll talk about be going over a version of the practice test. So you have an idea of what sorts of things you need to be able to do for the real one. And Monday, the 19th, there will not be class. That's the day that the test will be put out there. Okay. Oh no. Okay. Not sure what you're referring to.
I was talking about the pictures, the SOAR pictures.
Yeah. So, I imagine some of you look very different than your SOAR picture. Okay. So, and like for test 1, I will send a Canvas message to all of you, either like Sunday night or Monday morning, indicating what the password is for a test to safeguard against accidental entry. And then that message will also reiterate the particulars about the test, what it covers, time limit 75 minutes and so on. And then that test will run all through the next week. From the 18th to Friday the 23rd. But there won't be class Monday. There will be class that Wednesday. Okay. Now today's actually pretty quick. There's only a few problems to discuss, and each one does not take very much time, but an important concept nonetheless. Okay. Okay. So I'll get the screen share going. Okay. So there's a few concepts that I need to acquaint you with from this section. So the notion of dimension and rank, and then a related concept called nullity. Previously we learned about the concept of a basis. So a basis is a set of vectors that can be used to describe an entire vector space, because it has exactly the right number of vectors needed to do that. They're all linearly independent, so no vectors are redundant. So at least the number of vectors is not too large. And also the set of vectors of a basis spans the vector space. So it can describe all of them through linear combination. So therefore the number of vectors is not too small. So the number of vectors is exactly right. And every basis you can come up with for a vector space has the same number of elements. So Rn, the vector space we normally deal with, Rn, any basis for Rn has n elements. So we define the dimension of any vector space, as referred to as dim of V, where V is a vector space, is the number of elements in a basis, since it's always the same no matter what the basis is. So, example, the dimension of Rn is always equal to n, because you could use standard basis vectors, E1, E2 up to En are linearly independent, and they span the whole space. Okay. So now that we have this notion of dimension of a vector space, we can describe the dimensions of certain subspaces of interest, because subspaces are themselves vector spaces. So previously we saw the column space of a matrix is subspace spanned by the columns of A. So the dimension of the column space is called the rank of A. So it's the number of linearly independent columns that A has. And I should also mention that it's also equal to the number of non-zero rows in A after row reduction. Now, the rank, since it's dimension of a column space, is also called column rank. So that's the number of linearly independent columns. The row rank would be the number of linearly independent rows. But it can be proven that the row rank of a matrix always equals the column rank of a matrix. The number of linearly independent rows and the number of linearly independent columns is always the same. So we just have one term that's called the rank. So if you want to know the rank of a matrix, go ahead and row reduce it. However many non-zero rows you have left over after you've gone to echelon form, that's the rank. Okay. And then related to that, we have a nullity of a matrix, and that's the dimension of a null space of A. So recall that the null space of A is a set of all vectors such that AX is equal to 0. So that is a subspace. So its dimension is called the nullity. I'm not sure if nullity is actually listed as an official term in the textbook for this class, but it is a well-known term that's out there. So it's a convenient way to describe the dimension of a null space. So then the dimension theorem is a relationship between the rank and the nullity of a given matrix A. So if A is a matrix with any number of rows and n columns, that's the key here, n columns, the rank of A plus the nullity of A is always equal to the number of columns. So it's a way to figure out one of these in terms of the other. So as an example, if you have a matrix A, is let's make up a size here. Say 4 rows by 7 columns, and so let's suppose you reduce it to echelon form through row operations. And let's suppose you get only 3 pivot positions. So there's not a pivot position in every row, only 3 of the rows. Then what we can say is the rank of A would be equal to 3. So that's how many pivot positions are also non-zero rows that you would have. Therefore, the null space, you would take that rank and subtract it from a number of columns of A. So if a null space has dimension 4, that's how many free variables you have. So if you try to describe all solutions of AX equals 0 in a parametric form, then the dimension of a null space indicates how many free variables you would have. But that's something you would expect anyway for a matrix of 7 columns. If there are only 3 pivot positions, there have to be 4 free variables. Okay, so some of the problems, the exercises from this section about nothing more than just applying the dimension theorem to understand something about either a rank or a dimension of a null space of a given matrix. So the first problem right here. So a matrix A has 5 rows, 9 columns. So the number of columns 9 is very important, and it's asking for a rank of A based on this fact here. So we have the set of all vectors x, so that ax equals 0. That's a subspace, and if a basis consists of 7 vectors, then what is the rank of A? So this is testing your knowledge of not just the dimension theorem, but how you infer what the dimension of a space actually means. So the definition of dimension that's given here, and also the definition of a null space. So all of these concepts, definition of dimension, definition of null space, dimension theorem, come together in this question. So who could tell me, given this information about the matrix, what would the rank be? Well, someone give it a shot. What's the rank?
I don't know.
Sorry, what?
8.
No. All right, so this is one of the things that you're using. So this is, okay, here rank is what you're looking for. And n is the number of columns, so that figures into it. So the only thing missing here is dimension of a null space. Anyone? This statement here, subspace of all solutions of ax equals 0 has a basis consisting of 7 vectors. So what is this statement saying that would actually help us here? is this equation is the last step that gives you the final answer.
Is it saying that nullity is equal to 7?
Yes, it is, because subspace of all solutions of x equals 0, that's null space. Basis consisting of 7 vectors. That means the dimension, because remember, dimension is number of vectors in a basis. The dimension of the null space is 7. So therefore, what's the rank?
$16.
Our way. Or you have a wrong sign in your equation. Let's take a look at the chat here. Oh. Yes. Good job, Sydney. It's 2. Okay. So, all right. So null space dimension 7, A is 9 columns. So rank plus nullity is equal to 9. So because the nullity is 7, then we solve for, yeah, so rank is going to be number of columns minus the nullity. That's why I mentioned it in the wrong sign, is you added it when should have subtracted. Okay. Questions about that one? What about the next one? Here we have, again, we want the rank. And here's the information about the matrix. So what's the rank in this case? Anyone? Same idea.
Is it 4?
Yes, it's 4. Okay, so 8 columns total. Nullity is 4. That gets subtracted off, and what's left, that goes into the rank. Right, and the third problem is essentially the same. Here, instead of telling you what the nullity is in a roundabout way, and then you backtrack to the rank, now you go the other way. But here we have, you're given a rank, what's the dimension of the, null space. So that would turn out to be 7. So everything has to add up to how many columns are in the matrix. So for problems like these, if you're given the rank, you can use number of columns to backtrack to the nullity, or the other way around. Okay. All right, now the remaining problems work with rank and nullity also, but in a different way. Okay, so here you're actually supposed to construct a matrix. So there's a lot of variability here. That has a null space of dimension 3, and therefore has to have a rank of 2. So, so in this case, actually, this piece of information would not have needed to be given because here you're told that the nullity is 3 because there's 5 columns in total. then you would just get you'd have to have a rank of 2. So how would you go about doing that? There's a lot of ways that you can. So I'll just suggest one. So to account for the rank being 2, that means you have to have 2 columns that are linearly independent. So that's what you would have to do as a starting point. And this says nothing about what order the columns are in. You can, but you might as well make it like the first 2 columns. All right, so 2 linearly independent vectors. In this case, in R3. Why? Because the matrix has 3 rows. So you're going to fill a matrix with 5 vectors from R3 for number of rows. Now, choosing 2 linearly independent vectors, the easiest way to do that is two vectors that are not scalar multiples of each other. Actually, probably the easiest way to do that is you start by making a vector that is a scalar multiple. Like if you make up one vector, and by linearly independent, they got to be non-zero. So here's what you can do. You can take a vector and then double it so it is dependent, and then change one entry. Because if you have a vector that's a scalar multiple and then change an entry of it, it's no longer a scalar multiple. So that'd be one quick way to ensure that the 2 vectors are linearly independent. So that covers this part. At least that way we have a rank of at least 2. But you want to make sure that the rank is exactly 2. So now you have 3 more columns to pick. And the way you do that to satisfy these conditions, I choose any more free vectors that are linear combinations of the first 2. So, for example, you could multiply one of your first 2 columns by scalars, or you could add your first 2 columns together or subtract them. Any linear combination you feel like. That would guarantee that there are only 2 linearly independent columns. The remaining 3 columns depend on these 2. So by making sure that for rank, so the number of linearly independent columns is only 2, dimension of a null space has to be 3. There'll be nothing more to do at that point. You've chosen all 5 columns. You filled in the whole matrix in a way that satisfies this condition. And then by the dimension theorem, this condition has to be satisfied. You don't have to do anything extra to ensure this because of a dimension theorem. Rank is 2, 5 columns. The nullity has to be 3. And then finally, building a matrix that has rank 1. So a matrix that has rank 1 has only 1 linearly independent column. So what you can do is you have 3 columns in total to pick. And each column has to be in R4 because that's the number of rows. So you make a one non-zero vector, any non-zero vector, to be your one linearly independent column, and then you just take multiples of it. You multiply them by any scalars you like. 1, -1, 2, pi, anything you want. And then you'll have a matrix where all the columns are scalar multiples of each other. Therefore, only one of those columns can be linearly independent. Therefore, it has a rank of 1, and therefore also has a nullity of 2 because there are 3 columns in total. So if you're solving AX equals 0 with this matrix, because the rank is 1, you'd have 2 free variables. So these are how you can construct arbitrary matrices that are designed to have a certain rank and therefore also a certain nullity. Rank 1 matrices are actually very important in numerical linear algebra because of rank 1 matrices can be used to describe like small changes to a matrix. For example, changing one entry, for example. I should mention that we have in our curriculum, we have Math 326 and 426 that are all about like theoretical linear algebra, 426 being more advanced, and that's offered in the spring. Numerical linear algebra shows up in Math 461, which is being taught every other spring as a numerical analysis sequence, and also the graduate level. Okay, so questions about these two problems, where the job is constructing a matrix with certain properties. So that's the end of the material for test 2. So if you haven't already, I would encourage you to take a look at the practice test, especially now that all the material has been covered. And that's something that I will be talking about on Wednesday. So again, take a look at the practice test if you can, so that in case you have any questions about it. Now, what I've done here is I've chosen selected homework problems from the chapter 2 material, and that makes up the test. So there shouldn't be anything foreign in there about that. Okay, so I will end the recording at this point. If you have any questions, stick around. If not, you may scram.